Well, this lecture is on n-dimensional space, but I want to take a brief side tour first over last class. In the first place, many of you are being congratulated. Apparently the audience watching stuck with it more. They like audience participation programs. They watched your question with much more interest than the normal lecture. So congratulations. The second thing is I want to talk about something which I've said before and will say many more times. Luck favors a prepared mind. This is a quotation from Pasteur. I will say it lots of times. I regard it as reasonably accurate. Now, what this prepared mind means is you see more than the other people did. Yesterday's lecture was ostensibly what was said. There was that to be learned. But let's consider other things that you might have learned had you asked yourself questions. Like, to what extent does the opinions expressed represent the average difficulty I'm going to have in introducing machines? Another question you can ask yourself is, divide the class into two groups, those who participated and those who didn't. If you have to look for leaders tomorrow, where would you look at which two groups? Not certainly, but probably. Again, there are people who always sit in the back rows of classes. They're very smart, often the smartest person in class is back there. But if you want to look for the leaders, would you expect to find them there, or would you find them expected involved in the middle? Well, you want to ask yourself these questions. These are examples of getting more out of a situation than the average person does by asking more questions. Later on, you'll be better prepared to think about some topics which happen in front of your face, but you never thought. Now, this class on n-dimensional space is exactly the same thing. And I'll start again with a story about myself. When I came here after 30 years of being in Bell Labs, essentially in the mathematical research department, most of the time, I said, well, professors are supposed to think. They're supposed to digest knowledge and pass on the digested knowledge to the students. Well, what did I learn? So I put my feet on the desk a good many hours and contemplated what had happened to me. Slowly, I began to realize there was repetitions which I had never seen. Because I was in computing, and I was one of the few people who could cope with large-scale computing and had an idea what was happening, I was involved, more or less tangentially, but involved, in a great many large-scale projects. And I began to see, now that I was detached from the day-to-day activities, that there had been somewhat the same kind of trouble. I began to identify the same thing again and again. It took me quite a while. It did not happen in an afternoon. It took me a long while to realize the fundamental fact I'm going to say. You build three-dimensional things. The design space is n-dimensional. You design in n-dimensional space one dimension for every parameter you can adjust. Therefore, it is not three-dimensional space that matters in design. It is n-dimensional space. And n-dimensional space is vast, very, very large. And to convince you of this, I will start by your own experience. You think you know three-dimensional space, but you don't. You are really familiar with two dimensions. In two dimensions, a random walk will come back to the same place. If you meet a person, there's a good chance you'll meet them again. In three dimensions, that is not true. In three dimensions, say the ocean where the fish live, what do? They go around on the bottom, they go around the surface, they go around in school, they assemble at the mouth of a river, or they assemble at the Sargasso Sea or something. They cannot wander the open ocean and hope to find a mate. That's how vast three dimensions is. You can wander around two dimensions and sure enough you can get a mate, probably. In three dimensions, not very good chance. In higher ones, forget it. But that is a space of design. You're out there in that tremendously vast space. And the purpose today is to give you some feeling for this terrible design space, which is where the ideas behind what you have occur. Now, n-dimensional space is a mathematical construct, but so is three-dimensional. Now, let me review what you know in three-dimensional. I've got a nice block here, and I want to know the diagonal. I say, well, across the top, I apply Pythagoras' theorem, and I get the diagonal is the sum of the squares of the other two sides. Now, this other side is perpendicular to this. I look at that triangle. This is the sum of the squares of the other two sides, so it's the sum of the squares of the three sides. Or in general, in n dimensions, it must be that the distance squared is the sum I running from 1 to n of xi squared, where xi are the sides of each dimension. It's evident that's what is going to happen in n dimensions. A plane will be a linear combination of the x's, like a straight line or a plane in three dimension. A plane in n dimension will be out. A sphere will be all points a fixed distance away. These are the ideas we have. Now, I'm going to be interested in the dimension of n-dimensional sphere. I need a good deal of mathematics, and I have carefully not written down all the formulas I want because I tend to go too fast. And I have to drag you along to get you to feel what is happening. So I'm going to start with n factorial. Mathematicians can't cope with products very well. So we take the log. That's the sum of the logs of x, or we'll say it k running from 1 to n. The log of a product is the sum of the logarithms. Well, I took calculus. In fact, I even taught calculus. And I remember that sums were connected with integrals because the integral was the limit of a sum, right? So I promptly think of log x dx. It's a natural thing to think of. If I got a sum, it's connected somehow loosely with an integral. Well, this thing, the log is awkward, but I remember integration by parts was if I've got something I don't like the looks of, and it came from integration, if I choose that for my u, it will appear next time as a derivative, right? Remember? Okay, I pick u dv, and so I get x log x minus the integral 1 to n. The derivative of the log is 1 over x times the integral dx is x, just exactly x. This is x log x minus x 1 to n, which is n log n minus n plus 1. The log of 1 being 0, I don't get it there. So I have this expression. Now, I'm really interested in this. So I say to myself, if I take this integral and apply the trapezoid rule, I would have, well, 1/2 log 1 plus log 2 plus log n minus 1 plus 1/2 log n. Well, log 1 is 0, so I don't mind that half. To compensate and get the sum of all the logs, I will have to add 1/2 log n to this. And then I have this sum approximately that way. I've only undo it. And if I undo all the logarithms, I will come up with n factorial is approximately equal to n to the nth, the n log n term, n to the nth e to the minus n plus 1, which is near 1, but I'm going to toss in a constant c to cover the e, and it's going to turn out, because there's an error after all, it's going to turn out that if I were to go out to infinity and try and get the best possible fit, this would be the square root. Well, by the way, there's a half, so there's a square root of n in there. So this will turn out to be n to the nth e to the minus n square root of 2 pi n. Strictly approximating integral by a summation and turning around using summation to be approximated by the integral, I come up with something like that. Now, in the book, there are a bunch of table comparing actual n factorial with this formula by Stirling. And the table shows you that at 10 factorial, for example, you're up to 3.6 million. The ratio of the factorial to this approaches 1. But if you look at the table, the difference between the true answer and the approximation gets larger and larger. So one thing I have to answer is, how is it that although the ratio of the two numbers approach 1, the difference gets larger? I need it for other reasons also, and the answer is quite simple. If f of x is x plus the square root of x, and g of x is x, the difference is going to get large as x gets large. But the ratio is going to go toward 1, right? I have to get this across for several times. I'll need it in the future. I need this funny thing that two functions can differ in increasing amount, and yet the ratio approaches one closer to the other. Well, I have this, and now I have to cope with the factorial for fractional values. That's kind of silly. After all, factorial is integers. So we go to our boy Euler. Euler lived in the 1700s, and when he died, Gauss was about 6 years old. So Euler is well before Gauss. And Euler said he's going to introduce the function gamma of n is 0 to infinity e to the minus x, x to the n minus 1 dx. Now, if I apply integration by parts, dv and by u, I will get the integrated part, which if n is bigger than 1, it'll be 0 at the lower limit, it'll be 0 at the upper limit, and I will have e to the minus x over minus 1, which gets out, n minus 1, x to the n minus 2 dx, which is nothing else than n minus 1, gamma of n minus 1, and gamma of 1 is clearly equal to 1. So gamma of n is n minus 1 factorial. And you may ask, why didn't you change the definition to come up with n factorial? Well, Euler wasn't so dumb. When you get used to using the formula, you'll find out why the gamma factorial is gamma is n minus 1 factorial. It's a very convenient thing, although when you first start, it doesn't look like it at all. It's not bad. Now, I'm going to want gamma of 1/2. Gamma 1/2 is going to be that. Well, what do? I had calculus. I write x equal to t squared. 0 to infinity, e to the minus t squared. Dx is 2t dt. X to the minus 1/2 is a t down below. Now there's a 2, and I'm going to write this in a curious way. Minus infinity to infinity, e to the minus t squared dt. Okay. I cannot do that integral in closed form. It's well known that there's no closed form, but I can evaluate it by a trick. I will use a trick a second time today, and I quote Polya, who says, a trick used twice is a method. I'm going to write out for gamma of 1/2 times gamma 1/2, which will be the integral from minus infinity to infinity, e to the minus x squared dx, e to the minus y squared dy. And I remember something about double integrals. And I see an x squared plus y squared. I'm not stupid. I remember polar coordinates. Remember that? This is now in polar coordinates. This is going to be the integral over all space of e to the minus r squared, r d theta. 0 to infinity, 0 to 2 pi. The r goes from 0 to infinity. I go around the whole thing. I've covered the whole plane. That was the whole plane. Same thing. Now, this is easy to do. E to the minus r squared over 2 with a minus sign. And that's going to be the r integration, 0 to infinity. And the theta integration is going to be a 2 pi. This is going to be 0 at the upper limit, 1 at the lower limit, so I'm going to get exactly pi. So gamma of 1/2 is the square root of pi. A half, well, minus a half factorial will be square root of pi. I need that. I'm going to need it for a lot of reasons. Now I want to know the volume of a sphere in n dimensions, because I want to know how big it is, how much is nearby something. How big is a sphere of n dimensions? Well, I'm going to do this trick right here. Gamma of 1/2 nth will be, there'll be e to the minus first variable, second variable, so on. In n dimensions, it'll be e to the minus r squared. That is the radius of the shell. What is the surface of the shell? Now I've got to back off. A cube in n dimensions is clearly going to depend upon its side to the nth power, right? A sphere in n dimensions, the volume of the sphere is going to have to be some constant r to the nth. In 2 dimensions, that's pi r squared. In 3 dimensions, it's 4/3 pi r cubed, right? In 1 dimension, it's all the stuff along one line. It's just exactly 2, correct? So I know the general structure. What I don't know is this constant. But I say to myself, oh, that sphere. What's the surface? For a sphere, the surface is the rate of change of the volume. Right? The sphere is the rate of change of the volume? Okay. I want to integrate this by the surface area, which will be n Cn r to the n minus 1 dr. I'm going to integrate all these shells weighted by that over the whole range. That'll give me the whole volume of the sphere. Well, n Cn, and now I got to put r squared equal to t to get back to reasonable variables. E to the minus t, I will get an r to the n minus 1 over 2, a t. And dr is going to give 1/2 square root of t down below, dt. So this is going to come out to be a t to the n over 2 minus 1. And so this is going to be n over 2 Cn gamma of n over 2 minus 1, from which I can solve for this. And I find out, as you'd expect, that the volumes rise for a little while, but after a while, because the presence of an n, the volumes begin to shrink down. Spheres get bigger and bigger, about 5, 6 dimensions, and they begin to come down, 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 until at 2k dimensions, the volume at 2n will be pi to the n over n factorial. In 2 to n dimensions, that's what it's going to be. And you can see that pi to the nth only grows slowly. N factorial grows rapidly. It's headed for 0. The volume of an n-dimensional sphere, whether you allow me to make the volume as much as I want, is as small as I please. But that's not what's going to worry you. What worries me is how much is near the surface. How much of a sphere is near the surface? Well, it's easy. There's Cn r to the nth is the volume, minus that's a fraction. I'm going to decrease it by some fraction of the, say I take E being 1%, so 99% of the stuff, divided by the whole volume, will give me 1 minus E to the nth. I don't care how small you make E. I can raise n so that number approaches 1, correct? Almost all the volume is on the surface of a sphere of n dimensions. There's nothing inside. Take, for example, just in 2 dimensions is a circle. How much of the area is within 1/2 of the circumference? 3/4 of it, right? Right? In a volume of a sphere in 3 dimensions, 7/8 of the sphere is within 1/2 of the surface. There's only a little bit in the center. In high dimensions, I don't care how thin a slice you want. Let E be bigger than 0. This term is going to head for 0. I can raise n, so it's almost all the volume, no matter how thin a shell you want, is right near the surface. Now this is fundamental. It tells you in design space what you're looking for is almost certainly on the surface of the admissible design space. It isn't inside. All the calculus you learned won't do you any good, because remember, calculus only worked when the maximum or minimum was in the interval. When it's at the end, you had trouble, right? Now, it's not surprising. The best missile, the best airplane, the best anything you want will naturally push one or more of the parameters to the extreme. So when you're searching n-dimensional space for the best design, to a great extent, you are searching the surface. On linear programming, that makes linear programming very easy, because everything linear, you just track down the edges, you can find that. But for more variable things, there is no easy way of tracking around this horribly large space to find the best design. You may come down to a local optimum, but that doesn't mean it's best. For example, take North Jersey, where I lived so long. You want to find the lowest point. I'll tell you where it is. It's at the bottom of some mine shaft. How will you find it? Wandering around the surface? How will you find the mine shaft to go down to find the lowest point? You can't do it by wandering around locally. The same way in design. If you think you can use blind formulas for wandering around to find the best design, it is not likely. My experience tells me you need inspiration of where to look. Where to go out where the mines were and search around for that. If you don't think that the lowest point is a mine shaft, you're not likely to find anything near the lowest point. Well, design space sometimes has that property. There is something over here which is very good, and other ones over here, and there's not much in between. You can't simply walk from one to the other. You go up a mountain to get back to the next one. So this n-dimensional space, which you must search in for your design, is a very awkward thing. But you see, many of you are going to be responsible one time or other for the design, the acceptance of a new design of something or other. And if you believe what the manufacturer says, you deserve what you get. You don't want to believe what the person selling you says about something. You had better have your own somewhat ability to look through what they have done and raise questions. Couldn't a better design be found over here? What about this? Do you really believe that they have done the thing sensibly? Because it's this huge, vast space of n dimensions in which you are wandering around to find something resembling a good one. And I say again, it's almost surely on the surface, not inside. Yeah, let's see now. Can I find some more things? Now I want to start some more things awkward about you. I will skip over some material in the book because I don't want to bother too much in a class like this on mathematical derivations. I want to appeal to your intuition. We're in n dimensions, and I'm going to take the point from 0, 0, 0 up to the point 1, 1, 1, 1, 1. Now in 2 dimensions, it's easy to draw. (45 degrees). In 3 dimensions, it's up this way, and I think you know the angle is 60 between the 3 of them, right? What is it in n dimensions? Well, the point out to 1, 1, 1, 1, 1, that distance is the square root of n according to the formula I had here a moment ago. 1, 1, 1, 1, 1, add them all up, take the square root of n, correct? The cosine of the angle is the component on the axis divided by the length. Well, as n gets large, what happens? The cosine goes to 90 degrees, right? The diagonal is almost perpendicular to all the axes you had. Never mind what they told you in linear algebra about how to cope with n-dimensional space. We're talking about when we deal with real things with small errors. The diagonal can be, for sufficiently high space, almost perpendicular to all your axes. There's more directions. In fact, if you consider the points plus or minus 1, plus or minus 1, plus or minus 1 in n dimensions, there are 2 to the nth of those points, right? All the diagonals in every direction. Now, we're going to take the angle between two of them. Pick one of them and take the angle with that and another random one. It's going to be a sequence of plus or minus 1s times plus or minus 1s, added up, divided by the square root of n times the square root of n, so the angle, the cosine of phi between the two is going to be plus or minus 1, 1 to n, divided by n. That looks like what you remembered from the weak law of large numbers. An average of a bunch of plus or minus 1s is going to be 0, almost surely, right? Of course, sometimes it'll be 1, sometimes it'll be minus 1, but it's highly probable to be close to 0, right? That's saying that if you pick any one of those 2 to the nth, almost all of those directions are almost perpendicular. In n dimensions, there aren't just n directions which are almost perpendicular. There's something close to 2 to the nth, which are almost perpendicular to each other. You aren't going to be able to find a reliable n-dimensional representation in n variables, because the space has got these terrible properties which you know about. You can see you learned the vector analysis. These are exactly the things you learned when you took up vectors. And these were the things sitting at my desk, my feet up, wondering about what happened to me. I began to realize that this was the trouble. We couldn't do what we thought we could do when we took linear algebra. Maybe find a coordinate basis and represent everything like that. There are a bunch more almost perpendicular directions. And that's, since in engineering nothing is exactly right, you are really in trouble. Now, to convince you that you don't know what you're talking about in n dimensions, I got one more paradox, which I will need later on. I will need all these things later on. It's not just to baffle you. I've got a 4 by 4 box. I'm going to draw unit circles in each one. I'm going to draw a circle in here. If that's the origin, this is a point 1, 1. That distance is the square root of 2. Come down this way. This radius is 1. So the distance of that circle in there is square root of 2 minus 1. Now you're going to be ahead, so you might as well stop, and if you want to object, start saying so. Let's go on. In 3 dimensions, it'll be the square root of 3 equals the radius of the inner sphere in 3 dimensions. Right? In n dimensions, what's the distance from here to here? Square root of n minus the distance down. That's going to be the radius in n. Your last chance to complain. Anybody willing to argue about that formula? Can you see any way out of it? If you accept it, put n equal to 10. R10 is the square root of 10 minus 1 is greater than 2. That inner sphere is reaching outside the cube. It's convex. It touches all the spheres on the inside, but it reaches outside the sphere, outside the cube. I'm going to need that later on. 10-dimensional space is bigger than what you thought, but having 10 parameters is not an unusual situation. Correct? That's the design space. That's how ill-prepared you were by your education to look at your design space and ask yourself, what is going on? How shall I find my way around it? How shall I go about finding the best design when things like this can happen to me? That sphere reaches outside the cube, if you believe that formula. And if you think you can get out of that formula, start saying how you think you can get out of it. But that sphere is convex. It's tangent to all 1024 spheres in the corners. And those spheres touch each other. But the inner sphere is bigger. Yes, sir?
How can you still say that's a cube, though, in 10-dimensional space?
What? I build a cube in 10-dimensional space. Don't you believe in cubes in 10 dimensions? In design space.
Actually, but we're trying to visualize a 3-dimensional cube
Oh.
in 10-dimensional space.
No, you have to visualize a 10-dimensional cube in 10-dimensional space. It's from plus to minus 2 in every one of the parameters. Each parameter has a range from plus to minus 2. You've got 10 parameters, each one can run from plus to minus 2. Somewhere in that region you want to find a design. Now I'm making it very simple. In fact, of course, the design space is much more complex. I also need it for another reason later on. When I come to trajectories, I will point out to you that if these were tubes running along, I followed these various tubes from various initial conditions to the final one, something in between could be much, much bigger than you ever thought. And that the idea of thinking of trajectories as local tubes will not be an accurate representation of what you think is going on. In the case I had 28 variables. In Navy pursuit problem, I had 28 equations and 28 knowns to grind out a solution. And you can say, well, I start here, start here, start here. I can start with a whole bunch of points here. But what's in between has got that kind of a property and not the nice thing it ought to be in between. It reaches outside beyond them. Right? Things are not as nice as one could wish. But they're not hopeless. We, after all, do design. We do somehow arrive there. I must admit, when I look back at my experiences at Bell Labs on various missile projects or space flights and so on, I am slightly appalled at how naive we were not to have really thought of where we were. But then, when one is under the gun in engineering, having to get a project done, then rushing to another project, one doesn't take the time to think. It was only when I came here with the leisure of being a professor that I had the time to think, what on earth had happened to me during all those years? And this is the kind of thing in part. But I've been lying to you. It is not really design space. I've been talking to you and you've gone along with what we call Pythagorean L2 if you want. The sum of the squares of the differences is the distance. If you live in Manhattan, New York, or any other city with a grid, and you want to get from here to here, the distance is the sum of this plus the sum of that, right? It's not the diagonal. So there is L2, which is Pythagoras. There's L1, which is a sum of the absolute value of the xi minus yi. You look at the difference of the two coordinates, you add up all those differences, all those, and that's how far you have to go in 2 dimensions, in 3 and 4, and so on. And there's another one, which is widely used is L infinity, which is the max of the xi minus yi, where x is one point, y is the other point. It's the worst distance. It's the worst one you have to do. There's these three of them. Now, these are all metrics, what we call them. They're always positive or zero. They're zero only if the 2 points are the same. And they satisfy a triangle inequality. And they're symmetric. The distance from x to y is the distance from y to x. They're what we call metrics. These are all metric spaces. Now let's look and see what circles are. I need the red one for that. In L1, the sum of the coordinates is the distance. That is a circle in L1. In L2, of course, you know, it's like that. In L3, I take the maximum coordinate. When you're in design space, the distance is not always L2. Sometimes it's L1, sometimes it's L infinity, sometimes it's L2. Various distances and various coordinates are counted in varying ways. So, message I told you the sample space was, it's far worse because, in fact, you sometimes must have it within a given amount, period. Sometimes you want the sum of the deviations. Sometimes you want this. Therefore, you have a very, very real problem. Now, let me digress and tell you how things work and what L1, L2, and L infinity are really about. I will be outrageous. Pythagoras was the first great physicist. He discovered we live in L2, that the way to measure a distance from something to something is a standard Pythagorean formula. It works throughout physics. It works throughout data reduction. It's the principle of least squares. You're very familiar with it. But as I will point out to you when I come to the chapter on error correcting codes and such things, when I came there, I asked, what is the difference between two strings of bits? It's the number of bits that differ. It's L1. It's not L2. Strings of bits and things like that are best measured in L1. Now you as an individual, in making intellectual judgments, oscillate between L1 and L infinity. A child is coming down the street. Is that your daughter? No, it's too tall. That's an L infinity judgment. There's one measure is too big. Another, you might say, well, it doesn't look right. She's a little bit so much this, but there's too many differences. You count the differences, that's L1. Now, in artificial intelligence and such places where we're trying to measure patterns, to a great extent, they have gone to L1. They have gone to the sum of the differences between this pattern and that pattern when trying to match. They are not working in L2. They have found it inappropriate. Once in a while, they match with L infinity. Nope, that deviation is too big, forget it. That means that when you are working with typical physical situations in the past of building a missile or something, you are probably heavily in L2 and you are familiar. But if I get you into pattern identification, is that a friend or a foe? Or is that 6 airplanes coming in instead of 5? You are likely not to be working in L2, but you're likely to be working in L1 or L infinity, more likely L1. Therefore, these things I'm telling you about change the nature of the problem of searching in n dimensions from the convenient one you're familiar with to these kind of crazy circles. This is all right in L2, that's L1, that's L infinity. If you want to put outrageous, Hamming is a second-grade physicist. He says As Pythagoras Jr., he says, yeah, L2 is right for the physical world, but L1 or L infinity are what you want for the intellectual world. Most of the time. You don't want L2. Because L2 is so pervasive and so well developed, chi-square tests, least square fitting, everything else from physics, which is where it is correct. You tend not to think that in intellectual things, L1 is preferable, but I tell you, constantly in artificial intelligence and other areas of pattern matching, they have gone to L1 enormously and occasionally to L infinity. So you're in a different space when you are intellectual as against physical design. Now you're likely to think that you're designing physically, but as I said, when I have a bunch of airplanes coming in a pattern, I'm not in L2 in that pattern necessarily. I'm more likely in L1. The sum of the differences are more likely to control it. Therefore, you're going to find within your lifetime, but not much within mine, that you have moved more than you would have expected from L2 to either L1 or L infinity, and you will find that statistics does not support you. The chi-square test is a good example of an L2 fit. They haven't bothered to work out the L1 quality fits or L infinities. The mathematics is a little more ferocious. It's a little more difficult. But with modern machines, who cares about how difficult math is? We just let the machines grind away. They can do a few billion operations a second. What do I care? It is better to get the right problem solved a little bit slowly than to rapidly solve the wrong problem. I announce that as a very general theorem. The tendency is to try and solve the wrong problem elegantly and rapidly. And I've seen that an enormous time in my life, the grabbing for something I can cope with and solving the wrong problem, announcing this is the exact answer to the wrong problem. Generally speaking, I would rather have an approximate answer to the right problem. And that is where the difficulty arises, identifying the problem. The greatest step in creativity is recognizing that there is a problem. The second greatest step is identifying the nature of the problem. Pauli, one of the great quantum mechanics guys, says, once a problem is well defined, it's no longer of much interest to a physicist. Once the problem is well defined, then you can turn loose the mathematical tricks you've learned or can develop and solve it. But if you don't get the problem right, I don't care what you do about solving it. And I've seen a large number of wrong problems solved quite elegantly, and the great deal of time that's sometimes gone in to trying to shoot it down, or we have built the damn things and they didn't work. We built a whole mess of filters one time. They didn't work. They were the wrong answer. They were the right answer to the wrong problem. The necessity of getting the problem right is difficult. I come back to it. The fundamental problem you face is first, identify that there is a problem. There's a huge mass of problems around there which no one will acknowledge exists. Your business is filled with them. When you have found there is a problem and reason identified, then your problem is to identify it and make it more precise and say, well, now that is a problem like so and so and so and so, but it won't be. I will take up one day systems engineering, which effectively says there is no definite problem. And there isn't. Nevertheless, you have to start with a definite problem to do something. You can't work on the ill-defined problem, so you define families of problems and you begin to work around trying to do something. But it's a very interesting business trying to do it. Let me see if there's anything left or I can quit early. Oops. Now, I think I've said pretty much I have to. So let me summarize the situation. I want to end with this thing clearly in your mind. By and large, you are going to build things, you're going to handle things that exist in a physical world. By and large, the design of such equipment takes place in an n-dimensional space, not in 3. Much as you'd like to think that you can take ideas from your two-dimensional experience and think that they will apply to n dimensions, you will simply flounder and waste time and come up with bad designs. But n-dimensional space is so vast that even with fast machines you cannot explore all the points. If you take 10 variables, 10 values in each variable of 10 variables, you've got 10 to the 10th cases. You can't even look through it, let alone other things. So the idea that I can go at it in a, shall I shoot the cannon at everything and hit every possible target and look at every possible design, I cannot do it. It's hopeless. I must somehow search the space, which is so vast, where almost everything is near the surface. There isn't much inside. It is almost sure that your optimal design will be on the surface of feasible design, which, by the way, is not a nice square, it's not anything. It's got some screwy shape of what the feasible design region is. And design is a very hard problem. For example, if you make the wings, well, first, if you make the motor a little more powerful, a little heavier, I've got to strengthen the wings. And I've got to strengthen the body to hold the wings. And then because there's more weight there, I've got to make the wings larger. Then the wings have got to be strengthened again. So if I try to make a small change in some one variable, it reacts around the whole system rather rapidly. And it takes quite a while to settle down. So that small perturbations are very hard to cope with. But you must. If you design something to be exactly right, I'll tell you what happens. Take a central office which we designed exactly right to hold the maximum traffic. You put a little bit more down and the whole system collapses. Optimal design, when you exceed the limits, is terrible. Build a bridge which will exactly support 10 tons, and what happens when somebody walks across with a pound of candy in his pocket and it's a little bit more? Boom, the bridge breaks, right? Robustness in design is one of the things also which is generally not discussed and I have not said much about. But if your design is not reasonably robust so that it can stand a little variation, then you really cannot use it almost all the time. There are a few cases which you can, but they are almost infinitesimal. From weapons to guns to automobiles to blocking central offices, whatever you want. The optimal design will give you one which is seldom anywhere near robust. And it must be reasonably robust because the ideal conditions you're going to operate under are not realized. No way. Now, at lunch I was discussing the whole matter of testing with a friend of mine who's in the business of reliability. And I said, you know, you don't test the way you think. Take, for example, I know what happened to Nike missile. We ship the stuff out to Kwajalein. We get the equipment out there already. We know about 10 o'clock a drone is going to come by at about that altitude. It comes by, we shoot it down. One drone, once. Knowing when it's going to come, approximately where it's coming from, approximately the altitude. How good a test is that? But how many drones do you want me to shoot down? 10,000? You can't afford it. How do we get the people into space? Did you think we built thousands of missiles and tried them out to make them work? No, we did not. We do not test the way you think we do by repeated trials. We cannot, particularly with reliability. I get the vacuum tubes 1 week, and within a year we must commit ourselves and put down a cable. But we want the tubes to last 20 years. Any failed tube within 20 years will cost us $1 million for every failed tube. We've got about 1 year to test the tubes. That is what happened years ago. Now I will give you less time. As a new product comes off the production line, you want it in the field 3 weeks from now. How are you going to test for lifetime? It gets you back to design space. You're going to have to look at the design of that thing and from the design space figure out what you think the reliability is because you can't test it. There isn't time. You want the latest technology in the field tomorrow, but you want it to last 20 years. You can't test. This whole business of design and testing is an extremely difficult problem which you will face most of your career one way or another, either designing yourself or perhaps only accepting, or at the receiving end, using the equipment which has been sold to you. You're stuck with it. So I see you next week, and I will take up the subject of how do we represent information in machines, because that's the next natural thing.